Hey everyone, welcome back to The Explainer. So in part one, we covered the flexible, cryogenic world of flammable petroleum gases. But today, we're stepping into a completely different arena. We are looking at the highly hazardous, totally invisible threats of chemical gases. We're talking about cargoes where the danger isn't just a stray spark. It's about biology, chemistry, and catastrophic runaway reactions right there inside the tank.
Yeah, we're shifting gears. We're moving away from cargoes like LPG and LNG, which are mostly fire and cold burn hazards, to a completely different family. These chemical family cargoes can literally be lethal to breathe at concentrations you can't even smell. We're talking about liquefied ethylene gas, ammonia, chlorine, and vinyl chloride monomer, or VCM.
Let's start by looking at flammable versus toxic cargoes, because this is a really crucial distinction. Handling these toxic cargoes demands an entirely new mindset from the crew. Seriously, you cannot rely on the same instincts you'd use on a standard petroleum gas carrier. Think about it like this. With a hydrocarbon leak, your nose usually gives you a heads up, right? You smell the gas, and you might have seconds or maybe even minutes to react. Sound the alarm, get out of there. But with toxic chemical gases, a single breath can incapacitate you before your brain even registers that there's a problem. The leak is silent, it's often completely invisible, and it gives you absolutely zero grace period.
Okay, let's get into our first specific gas, liquefied ethylene gas, or LEG, which is a massive feedstock for plastics. So placing LNG on our cargo map, it boils at around -104 degrees Celsius. Because of that, it needs semi-pressurized, fully refrigerated Type C tanks. And as a major feedstock for polyethylene plastics, yes, it is highly flammable. But its deeper, trickier operational hazard is actually its chemical reactivity. The double bond between its carbon atoms can literally snap open and react. That means the real hazard isn't just fire, it's what the cargo might do to itself under the right conditions.
Next up is ammonia, which we can basically call the copper eater. Ammonia boils at -33 degrees Celsius, and it brings a really nasty dual threat. It has a narrow flammability band, sure, but more importantly, it is aggressively corrosive. It ruthlessly attacks copper, brass, and zinc alloys. So the big takeaway here is that if you accidentally install a single copper fitting or a brass valve, you have just engineered a slow, toxic leak directly into your own system. Every single component, every gauge, pipe, heat exchanger tube has to be made of compatible materials like steel or aluminum. Your cargo totally dictates your engineering choices here. On top of that, ammonia has this highly specific, very dangerous chemical reaction. If trace carbon dioxide, say from a contaminated inert gas supply you used for purging, mixes with ammonia vapor, it forms solid ammonium carbamate crystals. Now, this is not just some minor impurity. This carbamate is a powder that builds up and can fatally choke your pressure relief valves and small bore piping. And let me tell you, a blocked relief valve on a pressurized tank is basically your absolute worst case scenario. Moving right along to chlorine. This is the acid threat. Chlorine is so strictly regulated for toxicity that under the IMO gas code, cargo tanks are capped at 1,200 cubic meters maximum. Plus, they must be independent Type C tanks buried deep within the hull to protect against any collision. And here's why those rules are so strict. Chlorine's threshold limit value is a terrifyingly low 0.5 parts per million. Let that just sink in for a second. At 0.5 ppm, you can take a dangerous, incapacitating dose way before you can even smell it clearly. Human senses simply cannot be trusted here. You have to rely entirely on fixed and portable gas detection systems that can pick up concentrations all the way down to 1 ppm. So, quick question for you. If a small amount of moisture gets into that chlorine tank, what's the bigger risk? Is it a fire or is it acid corrosion?
The answer is acid corrosion. What's absolutely fascinating is that pure, dry liquid chlorine won't actually hurt standard steel piping at all. It's totally safe. But the very instant it touches water, a chemical reaction kicks off that rapidly forms hydrochloric and hypochlorous acids. And those acids will eat right through the ship's entire structural integrity in no time flat. So unlike hydrocarbons, chlorine's true enemy is moisture. Managing it means a ruthless discipline of dry seals, dry nitrogen purging, and keeping every single drop of water out.
Now let's talk about reactive gases and the massive risk of polymerization. So while chlorine and ammonia attack the ship's hardware, chemical gases like ethylene oxide and VCM do something even stranger. They attack themselves. First off, both are highly carcinogenic on chronic exposure. But operationally, the biggest nightmare is polymerization. It's an uncontrolled chain reaction. It starts with an initiation trigger, maybe heat, light, or a trace metal rust catalyst, that breaks open a molecule's double bond. Then comes propagation, where that broken bond attacks a neighboring molecule, linking them in chains. Finally, termination hits when the chains collide. But by then, a massive amount of heat has been released internally. It releases heat way faster than a sealed tank can possibly vent it, which causes the pressure to skyrocket in a terrifying runaway loop. Because of this totally self-destructive tendency, these cargoes require an inhibitor. It's a chemical additive dosed directly into the cargo to absorb those early reactions and suppress the polymerization. Because of this, there is an unbreakable commandment at sea: no inhibitor certificate, no loading. Ever. And you've got to monitor it constantly, because if you sail past that inhibitor's expiry date, or if unexpected heat burns it up faster than calculated, your safety margin silently vanishes, and you get absolutely zero visual warning.
All right, let's tie this all together with the 2.8 bar rule. With all these wildly different threats, toxicity, corrosivity, polymerization, what physical property actually legally classifies all these chemicals as liquefied gases under maritime law? Well, it all comes down to thermodynamics. Inside a sealed tank, the liquid cargo and the vapor sitting above it reach a saturation balance. At this exact equilibrium, if you raise the temperature, you automatically force more liquid to boil into vapor, which then forces the vapor pressure inside that sealed tank to rise right along with it. You aren't really controlling the pressure, you're controlling the temperature, and the pressure just follows the laws of physics.
Because of that thermodynamic reality, the International Maritime Organization had to draw a clear line in the sand. The legal gatekeeper for the entire maritime gas industry is exactly 2.8 bar absolute.
Under the IGC Code, if a cargo's vapor pressure crosses that 2.8 bar threshold at a reference temperature of 37.8 degrees Celsius, which basically simulates a worst-case hot tropical day, it is officially a gas cargo. Why? Because at that pressure, standard chemical or product tankers will literally crack under the strain. It legally mandates that you use a purpose-built gas carrier with pressure-rated containment systems. If you take propane, for example, at 37.8 degrees, its vapor pressure hits around 13 bar, so it is definitively an IGC cargo. So to quickly summarize our full map of gases, petroleum gases like LPG and LNG are your flexible or cryogenic fire hazards. But our chemicals are a different beast. LEG is a reactive plastics feedstock that needs extreme cold. Ammonia destroys copper and can choke your safety valves with carbamate. Chlorine demands absolute dryness to prevent horrific acid corrosion. And VCM? That requires absolute inhibitor discipline to prevent violent self-destruction through polymerization. Each one has a highly specific defining hazard. So, knowing the invisible hazards, the toxic thresholds, and those exact thermodynamic limits we just covered, you have to ask yourself a very serious question. In the face of a potentially fatal cargo substitution, where a slightly wrong chemical mix could either eat right through your pipes or push your tank pressure well past that 2.8 bar structural limit, are you going to blindly trust the loading paperwork? Or will you rigorously verify the chemistry and the physics before that cargo ever crosses your manifold? Because the safety of the ship depends entirely on your answer. Thanks for watching The Explainer, and stay safe out there.